My name is Zara Hodgson, and I lead one of the Innovation, Research and Development programs here at the lab. My talk today is Life, the Universe and Everything. And I'd like to propose to you that the UK has the answer to Europe's search for extraterrestrial life. But unfortunately for those galaxy hitchhikers in the audience today, I'm sorry to say that the answer is not going to be 42. Sorry. This is an image of Enceladus. It's a tiny, icy moon orbiting Saturn. And this image was taken by the Cassini spacecraft, which is in its final few months of its 20-year-long mission. And NASA recently announced that this moon, Enceladus, is a prime location for alien life. They've found the three vital ingredients: water, organic molecules, and a source of energy. And nuclear power has made this discovery happen. It's nuclear power and the energy from radioactive material that has allowed the Cassini spacecraft to fly through the geyser plumes of Enceladus and analyse their composition, identifying the presence of hydrogen. This is the final block, the final piece in the puzzle in establishing the potential presence of life. And it's plutonium, and more specifically the radioisotope plutonium-238, that's been harnessed by Cassini. And this has been in the form of small radioisotope heater units, or RHUs, to provide essential warmth, and larger radioisotope thermoelectric generators, RTGs, or batteries if you will, to provide power to the spacecraft's components, systems, and instruments, making sure that they operate over a long period of time in the cold and dark. And the Cassini spacecraft and its associated Huygens Titan lander has been fueled by 3 RTGs and 117 RHUs. So that's somewhere in the order of 33 kilograms of plutonium-238. But why use plutonium-238? NASA has used 155 kilograms of material over the last 45 years, and in many ways it is the ideal radioisotope for power source applications in space. And this is because the heat that it generates decreases by only a half over 88 years. So this half-life of 88 years means that you have a highly reliable heat and energy source with a predictable efficiency over very long periods of time. And this is particularly important where alternatives like solar panels won't work because you're too far away from the sun, or it's impractical, so the panels will be just too big and too heavy to launch. And plutonium-238 decays via the alpha emission process. So as we know, alpha particles can be stopped by a single piece of paper. So the shielding requirements are really simple. And importantly, the plutonium-238 has a high heat density, and that means that it's compact. So this glowing red pellet of plutonium oxide is about the size of a marshmallow, and 72 marshmallow-sized pellets is all that's required to fuel an RTG as used on the Cassini spacecraft, providing around 250 watts of electrical power. So for Cassini, they need 2 more sweetie jars of these large marshmallows, and then partially filled sweetie jar of the much smaller mini marshmallow side RHUs. So it's really effective, but there is a supply problem. Plutonium-238 is not a naturally occurring material, it has to be made. And this is made through the irradiation of another radioisotope, neptunium-237, which itself in turn has to be extracted from spent nuclear fuel. The USA has about 35 kilograms of plutonium-238 left. Russia doesn't have any for sale and possibly has its own supply issues, and Europe doesn't have a stock of the material either. So there's not enough for us to go back to Enceladus and carry out more detailed investigations above and below surface, or to explore Europa, which is another interesting moon that's orbiting Jupiter, or to follow up on whatever New Horizons has yet to discover in its ongoing mission. So what are mankind and scientists going to do to pursue our quest to understand the universe and understand how life started on Earth? Well, the Americans have restarted their plutonium-238 manufacturing program, but it's time-consuming and it's expensive. Other radioisotopes are available and may provide a solution, but that depends on the type of radioactive decay, the speed of that decay, and also the density of the power that could potentially be harnessed there. In 2009, the European Space Agency started looking at alternatives. They were looking for radioisotopes that had a comparable power density of plutonium-238, but didn't bring with it more onerous shielding requirements. They were also looking for a material that could be readily available and could also support missions of 20 years or longer. And in their studies, they have shortlisted americium-241 meeting those criteria that they set. It's better known for its use in the humble domestic smoke alarm with 0.3 micrograms per detector, keeping us safe at night. Now, americium-241 is known to accumulate in stored plutonium through the decay of plutonium-241. So it can be said, potentially, that americium-241 is abundant on the Sellafield site in Cumbria. And this is because we store over 100 tonnes of plutonium dioxide on the Sellafield site. And this is plutonium that's been separated through the reprocessing of the UK's Magnox and AGR reactor fuels. And we expect that there is somewhere in the order of 3 tonnes of americium-241 accumulating, or will be, already has been accumulated within this stockpile. So we've got a lot of the stuff. And it's a problem. Whilst the plutonium is an asset for the UK, the americium it contains is not. And this is because the UK wants to reuse the plutonium as mixed oxide fuels in new reactors. And the americium that's present can cause difficulty in the manufacture of the fuel and potentially could also have an impact on the efficiency of the fuel in reactor. So by removing the americium-241 and purifying the plutonium, we could potentially make the UK's reuse programme less time-consuming and slightly cheaper, and we could also power Europe's spacecraft in the future. So we have potentially here a win-win outcome, where we are converting waste into energy both here on Earth but also out in space. So on behalf of the European Space Agency, the team at UKNNL and our partners such as the University of Leicester started to ask ourselves, can we recover americium from the aged plutonium in the UK? And can we formulate a americium-fueled RTG? And the answer is, yes, we can. We have demonstrated the recovery of americium for real aged plutonium on the Sellafield site in a process that we've called AMPEX, americium and plutonium purification by extraction. And this flow sheet has been so successful that we've been able to produce americium oxide with greater than 99% purity and with an efficiency also greater than 99%. And the americium oxide powders that we've produced, we've sent to Germany, we've sent them to the European Joint Research Centre, ITU, in Karlsruhe, and for the first time they've pressed pellets of americium oxide, and we're waiting to receive those back shortly. And you can see on the Space Stone demonstration area that we've got a model of a prototype americium-fueled RTG. So with the process for extracting the material, we expect that we could be able to produce hundreds of americium-fueled RTGs or thousands of much smaller heater units from it. So we've got potentially a very good supply of americium-241. We've got a very efficient recovery process. So it's possible for the UK's americium-241 to power Europe's spacecrafts for decades to come. It can safely keep systems and potentially at some point people warm in the cold and darker space. So in our search for understanding life, the universe and everything, it is not 42 is the answer. It's some clever recycling of some nuclear waste in the form of americium-241. Now, our work for the European Space Agency has been full of light bulb moments all the way through, from that first idea about replacing plutonium-238 with americium-241, to the moment in the lab when we recovered americium oxide powder, and to where we are now with the pressing of the first americium oxide pellets in Germany. But we need to show that americium is a real and tangible power source. So in the next stage of our project, working with the University of Leicester, we expect to be able to produce the first electrical power from nuclear energy in Cumbria since the closure of Calder Hall power station. So that's going to be another light bulb moment for us.